Hi everyone, and welcome to our 21st lecture of CS2100 discrete structures. So in the last lecture we introduced the basics behind graphs, and in this lecture we will review some of the basics and as well do a couple of simple proofs about graphs. In part 2 of this lecture we'll do some more advanced proofs on graphs. So let's get started. So here we have a simple graph. And we'll go through a couple of basic definitions of terminology related to graphs. So a walk in a graph is a list of alternating vertices and edges where each edge connects its neighboring vertices in the list. An example of this graph of a walk would be going from Madrid through vertex 1 to Paris, and then through vertex 6 to Paris again, and then through vertex 4 to London. So that's an example of a walk in this graph. The length of a walk is its number of edges. So the length of this walk will be 3. And then a walk is so-called trivial walk if its length is 0. And if the first and last vertex are the same, then the walk is closed. A trail is a walk that has no repeated edges. And then a circuit is a closed trail. So an example of a circuit would be Rome, Madrid, Paris, Rome. A path is a walk that has no repeated vertices. A cycle is then a non-trivial closed trail in which the only repeated vertex is the first and the last one. So the circuit I drew is also a cycle. So these are some basic graph definitions and terminology. Okay, so let's look at how we would apply those on a simple problem. So the first question is this a simple graph? And the answer is no, because there are these parallel edges. So these are examples of these parallel edges. Then is V2, W1. So let's try to draw this. V2, W1, V, and then 8, and then Y, and then 10, X, and then 9, V. So the question is this a path in this graph? And the answer is no, because it repeats this vertex V. Is a trail? It is, because it does not repeat any edges. Is the closed trail? Yes, because even from this list you can see that it begins and ends with V. So is this graph an Eulerian graph? And recall the definition. It should not have vertices with odd degrees. And in this case, W has an odd degree because it has 5 edges coming out of it. Is there an Eulerian trail in this graph? The answer is no, because there are no more than 2 vertices that have odd degrees. So this illustrates how you can figure out answers to some of these simple questions on an example graph. So you should make sure to understand this. Okay, so let's do a simple proof on a graph. So here is a proof of proposition 5 from chapter 7. When an edge is removed from a cycle in a connected graph, the result is a graph that is still connected. And we're going to prove this using our direct proof strategy. So let's see how we will go about this. So let G be a connected graph that has this cycle V0, V1, V2, and then it comes back to V0. So we know from the problem that we're removing an edge from a cycle, right? So that's how we define that we have a cycle. Then let G prime be the subgraph obtained by removing the edge V0, V1 from G. So removing an edge from a cycle. Now to show that G prime is connected, we must show that every pair of nodes has a walk between them. And now we're going to assume that vertices X and Y in G are given. And because G is connected, we know there is a walk between them. And this is an example walk here, where consecutive vertices denote edges in G. Now, this edge that we removed, V0, V1, is either in this walk W or it is not. And now we're going to consider both cases. So case 1 is the easier one. So if the edge that we removed is not in W, then W itself is a walk from X to Y with edges in G prime. So it remains a walk, right, because we didn't touch it. So in case 2, if V0, V1 edge is in W, then this walk W with the edge V0, V1 is replaced by the walk V0, Vn, V2, V1, which is a walk from X to Y with edges in G prime. So the addition here is that this situation more or less looks like this. So we have some walk, and there is a cycle here. So this is a cycle, and now we remove this edge. So clearly, this node and this node still remain connected by a walk, which now leads over the cycle. So this is the definition behind this case 2 and why it works. So in either of these cases, there is a walk from X to Y in G prime, and so G prime is connected. And that concludes our proof. Okay, so this was our first proof example where we did a proof on graphs. So these proofs are a little bit more involved, and they involve, let's say, more text. So you have to make sure that you spell out how the proof proceeds. There is less mathematics in them, I would say. Okay, so let's see another proof. Let's say you want to prove proposition 4 from chapter 7 that says, for every connected graph G with at least one edge, if G has no cycles, then G has at least one vertex of degree 1. So in this case, we are going to try to prove the contrapositive of this, which says that for every connected graph G with at least one edge, if G has every vertex of degree at least 2, then G has a cycle. And note here that we don't have to consider degree less than 1, since no connected graph with at least one edge can have a vertex with degree 0. Okay, so let's see how we will prove this contrapositive. So let G be a connected graph with at least one edge and having every vertex with degree at least 2. So now we have to show that it has a cycle. How are we going to do this? So let's assume that n be the number of vertices in G and V0 be any vertex in G. So we are going to choose vertices to build the walk as follows. Since we know that degree of V0 is greater than equal to 2. We're going to choose V1 to be the other endpoint of an edge incident with V0. We know the degree of V1 is also greater than or equal to 2, so we are going to choose V2 to be the other endpoint of a different edge incident with V1. And then since degree of V2 is also greater than or equal to 2, we are going to choose V3 to be the other endpoint of a different edge incident with V2. And we can keep doing this until we reach vertex Vn to be chosen. So this walk uses n plus 1 vertices, but G has only n vertices. And so by our beloved pigeonhole principle, there must be subscripts I and j such that Vi is equal to Vj, which guarantees there is a cycle in G. And that concludes our proof. So here we did a proof by contrapositive that also involves pigeonhole principle, which makes it a really interesting proof.